I guess we'll get started. My name's Ewan Leith. I'm from a company called Reality Mine. I'll skip most of the stuff since Dave is also from Reality Mine. But we're a market research technology firm. We do data analytics and data processing. And today I'm going to be talking a bit about what we've learned from 5 years of building data warehouses on Amazon. We do market research on people's mobile phone usage, so how people use the internet on their mobile phones. Where we started. So we started with one physical server underneath someone's desk with a bunch of Fusion I/O cards underneath it. So it was really fast. It was pretty flaky if one of the Fusion I/O cards failed. We had to restore a whole bunch of data from backups. Eventually, we couldn't fit more Fusion I/O cards into the server. So we started looking around for what the other options were. So moved on from Fusion I/O, and we went to Redshift. So Redshift was a fairly new technology 5 years ago. It only just launched. It's a fairly traditional data warehouse. If you're coming from a normal data warehouse background, Redshift is kind of like all the other data warehouses. You have two choices of nodes. You can either have fast nodes or nodes with lots of storage. AWS call them dense compute or dense storage. Each node has a fixed ratio of CPU to storage, so you can choose either XL or 8XL large node, 8XL nodes. Each one of those nodes has kind of similar CPU to an EC2 instance, or a large EC2 instance. Is kind of the same as a Redshift large instance. You set up Redshift like a fairly normal data warehouse. So you have indexes, you've got temporary tables, you can do updates, inserts, deletes. Looks just like a normal database. But it also has this thing called table distribution, where you distribute the columns, you distribute the tables based on a particular column. So you have to pick a column when you create it, and you say, distribute this table on this column, and it gets spread across all the nodes on your Redshift data warehouse. This is pretty much fixed when you create the table. You can change it later, but it means shuffling the whole table, which, when it's a big table, is a problem. Redshift, probably its biggest strength is it supports really complex SQL. So any SQL you can imagine, Redshift will support it. It works on Postgres, compatible SQL, so it's kind of got a Postgres front end for it. But behind it, it's got the Redshift technology. So we were putting all this together, and we were doing daily data loads. So we would take our data from our SQL Server operational server in Rackspace, and we would transfer it over to Amazon S3 every evening. We would load it into the data warehouse, and then run a bunch of analytics reports overnight. For us, this was actually a really big improvement from Fusion I/O. We had this really cool Redshift data warehouse. We could do all sorts of really advanced internal queries. We were thinking, what can we do with this data warehouse? It deserves to be more than just an internal tool. So we decided we'd build an analytics platform. It was called Metis, but it's gone now. It had an interactive query builder, so you could do things like you can drag and drop boxes around and go, oh, I want to query people who do Google searches and compare them to Bing searches and what's the demographics. You could do dynamic filtering, so each time you change the filter, it would recalculate how many people were going to fit into your subset of users. It had really cool graphing capabilities, so you could get graphs of how people use the internet over days based on where they were, what they were doing, who they were with, all sorts of things like that. It really was a very nice piece of technology. But it didn't work. The technology didn't quite keep up with the vision. So Redshift at the time struggled a lot with concurrent queries. So Redshift had a query queuing system. It's significantly improved now, but at the time it effectively let one query run at a time. Now it lets you run multiple queries at once. Some of those queries are quite high latency, so we could be talking several minutes to run a query due to the volume of the data involved. And we were trying to do quite advanced SQL, so actually ended up being quite slow. And you couldn't really scale up clusters. So when you launch a Redshift cluster, you say, I want 4 nodes, 8 nodes, 32 nodes. You can't then just go, I want 34 nodes, 36 nodes, and increase it immediately. You have to create that cluster on demand. And to resize it, then you had to back up the cluster, restore it as a new cluster with a new size. Now you can actually add nodes to it. All this meant that the system didn't really work as we needed. Was a good idea, but it didn't work. So we killed that product, and we moved on. So what did we need next instead? So we were trying to do all this complicated SQL, all this complicated data processing, and what we decided was we needed faster data. We needed the data to be not daily data loads. We needed hourly or better, ideally as soon as possible. We needed more CPU power and on-demand capacity. So one of the issues we had with Redshift was that we had to preset all the systems that we were going. We would have 4 nodes, and we would run it 24/7. What we'd like to be able to do is scale up the CPU power itself as much as possible for 1 hour, and then get rid of it at the end, while still being able to query the data afterwards. We needed to be cost effective, if possible. We are a startup company. We don't have huge amounts of money to spend. So we looked into Apache Spark. So we went down to the Strata Hadoop conference in London, and we asked lots of people there, and we said, we're coming from a traditional SQL data warehouse. What's this big data thing? And we talked about what our use cases was, and basically everyone came back from Cloudera, from AWS, from Microsoft, all sorts of people said, you should look at this new open source project called Apache Spark. Everyone's getting on board with it, it's getting lots of vendor support. It's definitely the future. So Apache Spark, it's a big data processing engine. So it's in the Apache project, it's open source, you can download it for free, but it is really a collection of tools. It's not a product on its own. Lots of people do sell products based on it. So you can get one from Databricks, you can get Cloudera, you can get MapR. Microsoft have a version, Google have a version, and AWS have a version. So AWS have Elastic MapReduce. So Elastic MapReduce is essentially a way of building Hadoop clusters on demand, anytime you want. Scale up, scale down. It's fantastic. It's got really low operational effort. So we started as a team of 2 people working on our Apache Spark project. Neither of us hugely operational experts. And we very rarely had an issue in terms of the cluster issue itself. We had plenty of problems with writing Spark code, because it's not that easy, but the actual system itself was very reliable, very robust. So with EMR, the version of Apache Spark that gets shipped with Elastic MapReduce is slightly customized. So you have a thing called EMRFS. So along with the traditional Hadoop file system, HDFS, they ship a thing called EMRFS. This lets you store all the data in S3 consistently, so it uses DynamoDB to act as like a consistent file system layer on top of S3, so you don't have the general kind of issues with S3 where if you delete a file, it might still be there a few seconds later until it disappears later on. So we stored everything in S3 using a system called EMRFS, and we stored everything in these files called Parquet files. So if you've not come across Parquet files, this is probably one of the luckiest choices we made when we started the Apache Spark project. So Parquet files are effectively like a smart zip file. So they are object files with footers on them that tells you where data is inside the zip file. And it's column orientated. There's a few modern file structures that are being adopted. Parquet is one of them, ORC is one of them, there's a couple other ones, but Parquet has become effectively the industry standard. And you see a lot of new tools are also adopting Parquet. And this is one that we didn't really know about at the time, we just kind of used Parquet files, but as it turns out, almost everything out there now supports Parquet files. So we wrote a bunch of code. And it was kind of slow. And we thought, well, this is a problem. We spent a lot of time writing this code. It should be fast. And then we came across Spot instances. And because we hadn't heavily used AWS at the time, we didn't really know about Spot instances. So this was 4 years ago now. Turns out EMR supports Spot instances, and they're really, really cheap. If you've not used Spot instances, you definitely should. They are extremely cheap. And we just made the clusters big. I mean, it's kind of boring sounding, but we just made the clusters big. We went from going, oh, we've got 2 or 4 servers, and this is costing this much money, what do we do? To suddenly going, well, if we run 100 servers, it's only going to cost us this much, and we can be done in an hour. Well, that's great. Over time, we've actually improved the code performance, and things are faster now, but it really was that simple. We went from going, the cost is $5 per hour for this cluster, or $10 per hour for this cluster, to pennies per hour for this cluster, based on the Spot instances. EMR supports Spot fleets and all that clever stuff, so you can just say, I want this much memory, I want this much CPU. You should absolutely do it. And I can't remember the last time we lost a Spot instance due to the price increase. It does handle all that, but we really haven't had an issue in ages. So we took that Apache Spark project, an EMR, and we built our first data lake. So data lakes are sort of a cool thing. There might already be a backlash on them. But we built our first one. So we took Apache Spark, we took some on-demand reporting clusters, stored everything in Parquet, and we did hourly data loads to Redshift. So we switched from doing daily data loads with complex SQL to doing all the number crunching in Apache Spark on these temporary files. And we would output files in CSV for Redshift to load automatically. So Redshift could simply do an unload, load, straight into Redshift. No data manipulation in Redshift. It was just simply dumping the final version of the data into its system. That got us from 24 hours delay on data to 1 hour. This made a big difference to us. Then Amazon launched a thing called Athena. So Athena, if you've not come across it, is a serverless data query engine. I'm sure there's a cool name for it, but that's what it is. So it's a SQL engine where you pay nothing except for the queries that you run. So it's based on Presto from Facebook, so it's another open source project. Serverless, you don't pay anything while it's idle. You pay something like $5 per terabyte of data query, something like that. It doesn't cost anything. And it reads files from S3, and it's extremely fast. When Athena launched and we saw it could read Parquet files from S3 automatically, we were like, this is amazing. This is everything we wanted. It turns out Athena doesn't have the really brilliant SQL support that Redshift has. Redshift SQL is fantastic. Athena's is improving, and it's improving fast, but it's still not as complex as Redshift. So we saw this Athena tool, and we said we can do great stuff with this. We started using it all over the place with ad hoc tools. So we thought, let's build another data lake. This time, let's use Athena to do a lot of the work. It's going to be good this time. So Athena querying Parquet files on S3 was very fast but hard to query complex data structures. Because Redshift supports temporary tables and things like that, you could do lots of pre-processing of the data to make it easy for users. Athena didn't support all that kind of stuff, so users had to write fairly complex SQL to actually generate the queries. Over time, we kind of built a library of queries you could cut and paste in your right values. Then, AWS threw a curveball on us. As they do, they launched another feature, Redshift Spectrum. So Redshift Spectrum, Redshift, traditional data warehouse, fixed node sizes, reads files from local disk. Athena, serverless, reads files from S3. Redshift Spectrum uses the Redshift SQL engine, so you get all your complex SQL support. You get temporary tables, you get all that cool stuff. It looks like a normal data warehouse. You can hire a data analyst, say, this is Redshift, off you go. No bother. Redshift Spectrum supports scale-out queries and reads from S3. So now you can have Redshift reading local disk or Redshift Spectrum reading S3. You can do joins between the two. You can treat the S3 files effectively as local storage. It is extremely fast. One thing that's interesting about this is Athena, every query effectively gets the same kind of cluster size. So you run a query, the query gets processed, it's all magic, you don't see the cluster, and it's done. Redshift Spectrum uses the Redshift hardware that you're provisioned. So if you provisioned 4, 8, 32 nodes, your Redshift Spectrum queries get that much faster. So if you have a very large Redshift cluster, and people do have very large Redshift clusters, when they're querying from S3, each one of those servers individually is querying from S3, and it becomes extremely fast. So we decided to build a data lake again. The third time lucky. So AWS launched another tool that, again, really changed things for us. We'd done a lot of work at this point on schema management and how we could build things, how we could handle schema evolution, how we could change tables, how we could share the same data between Athena and Redshift. So at the time, they had separate table structures. You had to create a schema for Athena and create a schema for Redshift. Then AWS launched Glue. So Glue is actually a packaged version of Spark. But it contains a really, really useful thing hidden inside it. It should probably have its own name because it's that useful. So it has a schema management system. So you can point your Apache Spark clusters using the open source Apache Spark if you wanted. You can point Redshift and you can point Athena at this thing called Glue's metastore. And that lets you share tables between all these different systems. So when you create some tables, if you can have your Apache Spark cluster write some data to S3 and create a table saying this is the reference to that data. That data immediately appears in Athena and Redshift without any additional work by the Redshift DBAs or the Athena team. Just simply Spark goes, here's my data, and says to Glue, this is where the data is, and everything finds out about it automatically. It's absolutely fantastic. Glue has also got other stuff in it, but that's brilliant on its own. That alone would be enough for me. It also lets you run things like Spark jobs on a scheduled task, so you can say, here's a script that one of my analysts has written. Can you just run this at 3 a.m. every day and handle any errors? And it'll do that. If the script fails, it'll retry it and stuff like that. But the thing that I use it for all the time is this schema management system. It's absolutely fantastic. So we now have this data lake v2, which you can query from Athena, you can query it from Redshift Spectrum, and you can query it from EMR on Apache Spark. We're building an analytics platform. This time it is actually working. So what's next? So Redshift has always been fixed cluster sizes. So you have 2 nodes, 4 nodes, 32 nodes. What they've launched last week, so I can finally talk about it, is concurrency scaling. So now, if you have a query queued up on Redshift, you can set up systems so you can go, if this query is waited for 15 seconds, 30 seconds, don't wait anymore, go run on some magic Redshift cluster that AWS manage. And it just goes off and happens. If anyone tells me otherwise, it's just witchcraft. It's amazing. So this really does change Redshift a lot. So if you can configure it or not, you pay for it or not, it's a thing you can turn on, but it is absolutely a fantastic feature. So now you can have your fixed cluster size, and if you need more, it just works. So that was launched last week. Athena, I really want to tell you about Athena stuff coming up, but it's not launched yet. I was promised the end of Q1, but it's not. It's past end of Q1 now. But Athena is definitely working on new stuff. What I've seen in the last year and a half since Athena launched, I guess 2 years now since Athena launched, is that the Redshift team and the Athena team are clearly pushing each other. You see, if you speak to the Redshift team, if Athena launches a feature, the Redshift team are like, yeah, we're working on that and our one's going to be better. If Redshift launch a feature, the Athena team are, yeah, we're working on a better thing than that. You can see they are pushing each other, which is great for us as customers, because every time one of them launches a new feature, you just know the other one's going to better it. The downside of all this is data deletions need work. So we now live in a GDPR world. People have the right to have their data deleted or corrected. Today, if you want to delete data from S3 data files in Parquet, what you need to do is read all the files in, find the ones that contain the person's data. So if this person's been a customer of yours for several years, you might have several years worth of Parquet files storing data for that person. If you want to delete all that data, you have to read all those files in, filter them out, and write them back to S3, replacing the original ones. There are smarter ways to deal with it. The most likely one is crypto shredding. So effectively, you encrypt each person's data with its own encryption key. And then if someone requests their data deleted, you simply delete that key, and you can no longer read that data. However, that doesn't cope with people's right for correction. So if someone says, actually, the data you've got on me is incorrect, I want that updating, well, crypto shredding doesn't help there. So I'm sure there are teams somewhere inside Amazon working very hard on this problem, because it'll be a problem for everyone. But it is something that needs working. It needs improvement. So, conclusions. AWS Glue makes life better. Use it. It's absolutely, it's one of those tools where, like with KMS with S3, you didn't know what was missing until it was there. And then suddenly you're like, how would I live without AWS Glue? How would I live without encryption? It's that fundamental. This shared schema, even if you don't use anything else from it, use the shared schema. Apache Spark on EMR for raw CPU power. You cannot get better for big data processing. It's just really fast. There's nothing glamorous about it. There's nothing easy about it. It's not like a really simple tool where you just click a couple of buttons and your data will be processed. It's not got click and drag UIs. It's just really, really fast. And it is fast. And Redshift and Athena both work great. You can pick whichever one works best for you. If you need complex SQL, if you need temporary tables, if you have traditional data analysts, Redshift is probably the choice for you. If you've got very inconsistent workloads, if you have people who are a bit more willing to live on the edge, who are a bit more willing to work on the SQL and try and figure out how they can work within the constraints of Athena, it's absolutely fantastic too. We use both. We probably use Athena more, but we still very much are a Redshift company as well. So yeah, so thanks for listening, and any questions? Sorry. Oh, got a call. Do you want to shout? You have to shout from the back there.
Yeah, I've got one about partitioning. If you're using Parquet,
Yeah.
you also get benefit from partitioning. How do you go about that? You just use that when you tend to use the doing project uses streets. So we've got a partition by hour at time. So that you struggle with partitioning.
Yeah, so partitioning. So in EMR, or in Parquet files in general, you partition the files by essentially a key value that controls where it's stored. So Parquet files are actually collections of files. And you do have to choose a partitioning, and it does matter. So we started on hourly as well. We now do hourly plus like an identifier to kind of split people out into different buckets. Because we found that hourly was too inconsistent, because you would have an hour where actually nothing much happened, and an hour where someone has done loads of work, and the bucket sizes would be too different. So we've now started bucketing people as well as splitting them by hour. Sorry.
So Athena and Redshift were sort of implementing the same features.
Yes.
Why internally do they have this in Amazon? And if you're starting fresh, what would put you in either direction?
I don't know why they do it. I like that they do it because it does definitely push them on. I think in part, I mean, if you were very cynical, you'd say that Google have a serverless data query engine, so Amazon probably went, well, we need a serverless data query engine. Because at the time, I remember when...
So it's for that elastic use case there?
Yeah, so the elastic use case. I think that's why AWS probably built it, just so they could say to Google, no, you're not the only ones with a serverless data query engine, we have one too. But actually, both are very, very good. I think if you were starting out, I would probably say start with Athena, just because you don't pay for it. You know, it's very cheap to start with. Athena has drawbacks, like we have on several occasions run up several $100 bills from someone running one query, where they've left off the partitioning query. And like 45 seconds in, they're going, this query's taken a while, isn't it? And then they go, ah. And in that 45 seconds or a minute, it's queried terabytes of data. It's really fast. So they have actually just added cost controls in Athena. So you can now say this user group can only spend this much money. But that's the downside of Athena. Anything else? Oh, sorry.
This might be out of scope for it, but does it handle anything with row-level security?
It has some row-level security work, but it's not. Doesn't work for us. But it has kind of the tick box of row-level security. You can say, here is row-level security, but it didn't work for us.
So on that subject, could you use the Glue technology to have various segregations of data across multiple Redshift?
Absolutely, yeah. Redshift Spectrum only supports one external schema, but inside that you can have multiple different segregated sections, yes. Sorry.
So when you're designing your data lake, let's assume you have multiple different types of data that you're ingesting coming from multiple different sources. Would you separate those into different S3 buckets to make it easy to query against those individual things, or does that make it more complicated to then join those data sets up later?
It does make it more complicated, but it actually also makes it faster. Because obviously you start hitting kind of bandwidth limits and API limits on individual S3 buckets if you get very large. So yeah, so it does make it harder to use multiple buckets, but it's probably better to use it. Okay? Well, thank you all very much.